Hi everyone, I'm Sagar Sudhakara, one of the co-author of Thompson sampling for linear quadratic mean field teams paper. So let's get started. So we see networks of interacting agents everywhere. So what are the salient features of this kind of ubiquitous networks? They have large bar growing size and agents have local state and they can have coupled dynamics and cost. The main design challenges of these ubiquitous networks are scalability of the solution and how to handle model uncertainty in this particular networks. So outline of today's talk is first we are going to discuss about the system model, then we are going to move into the planning solution, and then we are going to discuss about the learning solution along with conclusion and numerical results to concur with the above solutions. Now coming to the system model. So we have a mean field team model where we have heterogeneous agents, that is agents of different types, and different types is denoted by capital M, and NM represents the set of agents present in that particular type M. Now, the empirical mean field x bar empty and u bar empty of agents of type M is defined as the empirical mean of the state variables and the control action variables for that particular type M. So they are represented by x bar empty and u bar empty, which is nothing but the empirical means. And collection of this empirical means of all types is represented by bold letters x bar t and u bar t. Now, system dynamics of agent I of type M is represented by this particular equation. We see that the state xit plus 1 is dependent on the current state and action variable as well as the empirical variable x bar t and u bar t plus a local noise and a noise common to just that particular type plus a global noise. And per step cost can also be decomposed as the means part as well as the relative part, and it is represented by cxt comma ut. We see that it is dependent on the current state and actions as well as the empirical state and action variables. So our main objective is to choose a policy pi, which is nothing but a function mapping from the state variables to the action variables, which tries to minimize the long-term average cost, which is represented by j pi of theta. So our aim is to find a j of theta, which minimizes this j of pi comma theta over all policies. Now, we're getting into the planning solution for mean field teams. We're directly solving the linear optimal control problem requires solving a high dimensional Riccati equation. So more efficient solution will be based on decomposition of a system into mean field and relative system. So when we decompose the above system into mean field system and relative system, the dynamic part also decomposes into the mean part as well as the relative part. We see that the dynamics of the mean part is dependent on the empirical mean of the current state and actions plus the empirical mean of the noise variable. And even the cost function can be decomposed into the empirical mean part plus the relative part. So for the relative system, for any agent I of type M, we see that relative state and actions is defined nothing but xit minus the empirical mean plus and u brev it is nothing but uit minus the mean u bar empty. And the dynamics is provided in this particular fashion. We see that now the dynamics are only coupled by the noise variables, where leaving the noise variables, they are all decoupled. Even the cost function is decoupled. Now, planning solution for mean field teams. Under standard assumptions, the optimal policy is given by UIT equal to L brev M x brev IT plus L bar M x bar T. So L brev M and L bar M is obtained by solving the Riccati equations. That is, now instead of solving Riccati equation of very high dimension, we just have to solve M plus 1 Riccati equation of a very smaller matrix. So that is the main advantage of our planning solution. Now, getting into the learning for mean field teams with unknown dynamics. The model dynamics is unknown and we need to design an adaptive policy which asymptotically converges to the optimal policy. So we compare our learning algorithms with other algorithms by obtaining the regret. Regret is nothing but cost of learning algorithm at time t minus the cost of clairvoyant agent at time t, summing over all of this over time horizon capital T. And we see that directly using existing algorithms like Thompson sampling or OFU or certainty equivalence methods, we obtain a regret which scales by n to the power 1.5. So regret per agent grows with size of the mean field network. So we have to come up with a method which doesn't scale with n. So separate learning for mean field and relative system. So we have a separate Bayesian priors on parameters of mean field system and relative system. And we have a learning algorithm with two parallel subroutines for mean field and relative system. So using mean field subroutine, we compute U bar MT, and using relative system subroutine, we compute U bar YT, and we combine them to compute UI of. Now, learning for the mean field system. So the learning subroutine for the mean field system is by starting by obtaining our posterior. We update the posterior based on the mean field state and action history. And then we have an episodic kind of algorithm where algorithm proceeds in episodes of dynamic length. And the episode triggering rule is every episode K ends if the determinant of covariance falls below half of the value at the beginning of the episode, or if the time spent in the current exceeds the length of the previous episode. So that is the episodic algorithm which we are using. And at the beginning of each episode K, we sample the new posterior P bar, theta K from the posterior P bar, and we compute L bar of theta bar K and return L bar X bar T. Similarly, for the relative system, we have a separate posterior over theta brevem, and based on the relative state and actions, we compute this posterior, and we follow the same kind of episodic thing which we used for the mean field system. At the beginning of episode K, we sample theta brevem K from the posterior, and we compute now L brevem, which in turn is used to compute U brev M of T. Now, once we do the learning subroutines for a mean field and relative system, we are able to now compute UI of. So we have this particular standard assumption, that is to ensure that the closed loop dynamics of the mean field state and the relative state of each agent are stable. We have this particular two assumptions, and here we are using the induced norm. Now, once we do all this, we compute our regret, and under standard assumptions, the regret of a proposed algorithm, TSDEMF, is upper bounded as follows. So we see that the regret of the proposed algorithm is bounded by big O of m to the power 1.5 root t, irrespective of total number of agents. So the following special cases are of interest. For homogeneous systems, that is for m type is equal to 1, we have regret, which is nothing but provided in this particular equation. We see that the scaling with number of agents is big O of 1 plus 1 by n into root t. So the regret per agent reduces with the size of the mean field system compared to the other algorithms where the mean regret per agent were increasing with the size of the network. So that is the main result which we are obtaining in our paper. Now coming to the numerical examples, we have a mean field system. So we compute the regret over time, and we have plotted in this particular graph, and regret by root t with respect to time and plotted with this in this particular graph. We see that the regret reduces with the number of agents, and R of t by root t converges to a constant. So this shows that empirical regret matches the upper bound of big O of 1 plus 1 by n into root t, which is obtained in the theorem. And we also compare our results with the naive TSD algorithm. So if we use well-known algorithms and we compare our results to their result, we see that the regret of our proposed method reduces with the number of agents n, while that of the other method increases with. So the summary of our paper is we provide a planning solution which solves smaller m plus 1 Riccati equations which are of lower dimension, and we proposed a new Thompson sampling based learning algorithm which exploits the structure of the system model, and we provided an expected Bayesian regret with agents of m different types at time horizon t, and it is given by big O of m to the power 1.5 into root t, irrespective of the total number of agents. And for homogeneous agents systems, that is for m is equal to 1, we provide a regret per agent which reduces with the number of agents, that is big O of 1 plus 1 by n into root t, and doesn't grow with the size of the network. Thanks for attending the talk. Thank you.